detecting and mitigating illicit cryptomining on continuous integration services platforms. In this work, we discovered a new type of cryptojacking on CI platforms. We are going to present our work from these four aspects, including the background and the threat model of our work, also our measurement and mitigation processes. With the emergence of cloud-native computing, DevOps becomes more mature and practical for automated developers. DevOps is a set of practices that combine software development and IT operation. There are many commercial CI platforms such as Circle CI and Travel CI, which achieve DevOps and have a lot of users. All these platforms offer continuous integration and continuous delivery tools, and also provide abundant computing resources. By cooperation with the code hosting platforms, such as GitHub or GitLab, CI platforms can help users achieve automatic code build, test, and delivery. Now we are going to introduce how CI platforms interact with code repositories and users. Firstly, users need to create code repositories on public code hosting platforms, such as GitHub, GitLab, and Bitbucket. Secondly, users can log into the CI platforms with the account of these public code hosting platforms and authorize CI platforms to access their repositories. Thirdly, users set up the CI workflow in a configuration file. The configuration file is usually included in the code repository. Different CI platforms may require different formats of the configuration file. On the other hand, the configuration file contains a set of jobs, specify the workflow to build or test code in the repository. Last, according to the configuration file, CI platforms run all jobs in a visualized environment, such as a container or a virtual machine. The users can trigger this job by some operations, such as committing to the code repository. Users can also start the workflow manually through the CI platform's API. After the job are executed, users receive a notification which includes the status of the jobs and other information. After visiting commercial CI platforms, we found that nearly all CI platforms provide free trials to attract new users. Users can then access rich resources managed by the CI platforms. Unfortunately, malicious users can abuse these resources. Lots of adversaries conduct crypto mining on these CI platforms for profit. Like benign users, adversaries can directly start a mining job as a standalone job in the workflow. For example, in this figure, we can see the adversary set up a job in the configuration file for downloading and running a mining tool. However, this kind of injection is easily detected by the CI platforms. Instead of straightly starting a mining job in the workflow, the adversary can opt for a stealthier way to hide it behind a seemingly harmless job. As shown in this code snippet, mining commands can be inserted into a job for Docker image building. The mining program will be launched and activated by the Docker build. Also, the adversary can prepare a Docker image containing a mining command. When this image is used for testing, the mining processes will also be launched in the test step. Usually, a code repository only uses one CI platform. We wrap the corresponding connection between one CI platform and one code repository with mining job as a CI jacking instance. However, to maximize the revenues, adversaries can create many accounts on code hosting platforms to launch multiple mining jobs on one CI platform. Please note that opening accounts is trivial for adversaries. since it only needs an email address and passing a captcha test on Google. Thus, the profit margin of CI jacking is huge. Moreover, the adversaries can connect multiple CI platforms to one code repository. Once the workflows are triggered, the mining job will be launched on all connected CI platforms at the same time. This boosts the profit gained by one code repository. Since CI jacking requires the cooperation between code repositories and CI platforms, we can then trade CI jacking instances from both code hosting platforms and CI platforms. For example, this code repository with mining job has multiple CI jacking instances. Because it leverages 9 CI platforms, we are going to inspect these configuration files. On the other hand, we analyze the logs of job executed by the CI platforms. This log also can help us trace the CI jacking instance. From the code hosting platforms, since all jobs to be executed by a CI platforms are defined by the CI configuration file in code repositories, a crypto mining job, if it exists, must be triggered by the commands in this file. Thus, we firstly collect CI-related repositories and their associated configuration file from GitHub. Then we parse the command that will be executed on the CI platforms and use a set of regular expressions to check their parameters. After identifying the key parameters such as wallet address or mining pool address in the command, we will flag the related repository as illicit. CI platforms can also provide data for cryptojacking discovery. Usually, CI platforms monitor the progress of each CI job, recording its runtime statistic data related to CPU, memory, disk, network, and I/O. The output of crypto mining jobs may appear in the CI platform's logs, including the notification of hash rate, the connection status of network, the feedback from the mining pools. Also, using a set of regular expressions to identify the intermediate metadata produced by the mining jobs, the related repositories will be flagged. Now, let me summarize our findings in the measurement. After checking 500,000 GitHub repositories, we flagged 894 of them as suspect, and after the manual validation, 96% of them are determined as malicious. These malicious repositories has launched about 200 CI jacking instances on 23 commercial CI platforms, including the 104 wallet addresses and the 71 mining pools. Looking into the wallet addresses and the mining pool domains, 13 kinds of cryptocurrencies are involved in CI jacking. Among them, the Monero is the most popular cryptocurrency because it can bring the highest revenue to adversaries. Based on our estimation, the total revenue of the Monero CI jacking instance from March 2017 to May 2020 is nearly $800,000. Let's now look at the temporal data. View all malicious repository. The earliest CI jacking related GitHub repository are created in 2014, but the first CI jacking instance shows in 2017, and the large-scale explosion of CI jacking starts in 2018. Also, the growth in the number of instances is closely related to the dynamics of the cryptocurrency's prices. Taking Monero as an example, a large number of instances appears with the price moving towards its peak, and such growth starts to slow down with the price going down. But undoubtedly, new CI jacking instances still appear in the CI platforms every day. Although the CI platforms has some mechanism to detect and block adversaries' accounts, adversaries can still easily create new accounts to continue the CI jacking. As long as the adversary can make money from the CI jacking, this account creating blocking circle will continue forever. To kick off hijacker from CI platforms, our mitigation works on downgrading the performance of CI jacking instances to make them unprofitable. Now, let's focus on the mitigation strategy. A key observation is that crypto mining jobs have to finish the task assigned by the mining pool within a given time window. Otherwise, they will receive nothing in return for the computation spanning that window. However, almost all legitimate jobs in the CI platforms don't have this limitation. Following this line of thought, we introduce jitters to the jobs on the CI platforms. Such jitters satisfy two requirements. First, jitter cause significant and robust delays in the crypto mining job, such that miner can't profit. Second, only moderate overhead is introduced for the legitimate jobs. Blind injection of jitters may not work well, which forces serious delay in benign operations. Alternatively, we should introduce jitter just for mining jobs. Since hash operations incur high frequent visits to a certain memory page, this serves as a good signal for mining job. So firstly, our mitigation profiles the memory access of the target job. After locating a suspicious memory page, our mitigation injects jitter to each access. Specifically, our mitigation firstly uses the mprotect system call to remove the access permission of the target page. When this page is accessed, a segmentation fault will be triggered. The jitter is injected here to generate a delay by calling the function sleep. Finally, the permissions are set back in the signal handler to make sure the job executing right. We evaluated the effectiveness of our mitigation against all cryptocurrencies appearing on the CI platforms. This figure shows, with and without our mitigation, the hash rate for using different mining tools to do the mining on different cryptocurrencies. And the black part in each bar shows the hash rate decline introduced by our mitigation. Also, we call it as the delay ratio. The hash rate of mining all cryptocurrencies was reduced over 95.3% on average, and all mining become unprofitable. We also want to know how our mitigation affects legitimate jobs. So we evaluated the performance impacts of our mitigation on Parsec and Spec 2017 benchmarks. The results shows that our mitigation introduced low performance overhead. The overheads on 18% benchmark are below 10%. For the remaining benchmarks, our mitigation introduced an overhead between 10% and 15%, since they are all characterized by relatively intensive memory accesses. To evaluate the performance impact on real-world CI job, we randomly sampled 200 CI jobs and measured the elapsed wall time of individual CI job when running them with and without our mitigation. In summary, the evaluation shows our mitigation only introduced about 10% relative overhead to most CI job, and thus has low impact on developer productivity. Thank you for the attention you have given to me.